Thank you very much. Yeah, so I'm Coulomb from Kansas State University. And it's my pleasure to tell you about our recent work on Coulomb explosion imaging. We are from the gas scale community, so what we do is slightly different. So instead of a complex system, we look at like one single isolated molecules at a time and try to sort of image the molecular structure and also try to image the motion of the atom within the molecules. Um, so first of all, what is Coulomb explosion imaging, or short we like CEI? Basically, the idea is very simple. Like we want to ionize the molecules, we remove many electrons, and then the molecules get highly charged, and then we start to dissociate into multiple ions because of the Coulomb repulsion, and then we measure the fragment ions, and then from the momentum of the fragment ion, and from there we try to deduce the information about the molecular structure. And Coulomb explosion imaging will pioneer in the context of like you have the ion beam in a collision with a twin coil, and then basically the collision strip out the electron from the molecule, the ions, and then you basically the same, you measure the momentum and then try to deduce the information about the molecular structure. However, if you do this in this setup, it's very difficult to perform any time result measurement because like you need to accelerate the ion beam, and it's hard to introduce the time result measurement in here. So in the late 90s, where we have ultrashort lasers, and also nowadays we have intense ultrashort X-rays, then we can think about how we can follow the structural changes. So basically, because the X-ray or the laser is ultrashort and under instance, so we can ionize the molecules, like remove many electrons and remove it fast. And it's also with the time resolution, so you can induce the dynamics by one laser, and then you measure the structure of the molecules with another laser, and hey, what's it going on? And then nowadays we also develop a high repetition rate laser and X-ray, so we have like more statistics. So this is an example that I will come back to the data later on, but let's say we can induce some molecular motion, and then you can try to image those motion of the atom within the molecules. The example on the right is like from earlier, like one of the first work using laser to image the molecules. So basically here they have the iodine atom, iodine molecules, and then they use one laser to excite it into the first excited state. And because it is repulsive, then the molecules start to dissociate. And then at a delay time, they come up with a second punch called the probe punch, where they ionize the molecules into like and dissociate into two I plus fragments, and they measure the kinetic energy of these fragments, and then they can deduce back the so on the x-axis here, like the distance between the two iodine atoms, and then the distribution, and basically the spatial distribution of the atom. So as you can see, as time goes by, in sort of like 100 femtosecond time scale, you can see how the two iodine atoms move away from each other. So if you compare Coulomb explosion imaging to other structural dynamics method, it provides high temporal resolution and also high sensitivity to light atoms such as hydrogen and protons. And it gives like access to three-dimensional information because the momentum is better, right? So, however, you need to detect like multiple particles together, like in one event, like on coincident measurement, and that measurement is very challenging because like the detector efficiency is not very good, and the red ray will low and things like that. So most of the time result CI studies have focused on only 2 or 3 body fragmentations, which limit the size of the molecule system that you can address. So how do we deal with the bigger molecules? So recently, last year, there was a recent result from the European X-ray free electron laser led by Boll. So they look at, I think, one of fairly big system in the CI context. So they have like 11 atoms. These molecules called ionopyridine. So it have the iodine here and the nitrogen here, and then the carbon and the hydrogen. So they use intense ultrashort X-ray like 2 keV, and then they ionize these molecules and dissociate it into multiple fragment ions. So to present the data, they normally we use we align the momentum of one ion to the x-axis, where we call it is in the x reference, and then because like it's a gas phase, so the molecules randomly oriented, so you have to rotate the data in such a frame so that it overlaps with each other. And then they put the momentum vector of the nitrogen ion on the upper plane like this plane, and then they plot the carbon and the proton in this frame of reference, and here you can see the results. So the iodine atom is on the x-axis, which is not plot here, and then the nitrogen is on the upper xy plane, and then you can see if you refine, they say one proton to be detected, at least one proton to be detected together with the iodine and the nitrogen, then you can see this distribution, and this distribution corresponds into the 4 hydrogen atoms of the molecules. And they can do the same for carbons, and then you can also see the 5 carbon corresponding to the 5 carbon of the molecules. However, like this is momentum space, it's not real space. So this carbon get, because of the Coulomb repulsion from the iodine, it get pushed back to the center. So that's why you see it here. But it gives very detailed information about intermediate size molecules of around 10 atoms that we haven't been able to tackle before until now. However, the access to X-ray free electron lasers is pretty limited, so we can submit the proposal, maybe get a week or two of beam time every year. So we ask ourselves like whether can we achieve similar results using the tabletop laser, where we have access like 24/7 in our lab, and then also like this is just one the example before it just for planar ring molecules. So we asked the person whether we can look at like different molecular structures also, because if we want to induce the structural change from let's say the ring molecules to something that is not planar ring molecules anymore, then can we do that? And of course, like when the molecules in no longer in the one plane, then we have to look at the full 3D momentum space instead of the projection on one plane. And of course, like the ultimate question, like can we really make molecular movies that so of structural changes, that so like how the atom move within the molecules. Okay. So this is the setup in our lab. We use very standard high sapphire laser, 800 nanometer, 25 femtosecond, running at like 3 kilohertz. We focus the laser to the peak intensity around 10 to the 15 watt per centimeter square, and then it will interact with our molecular sample. Normally we look at like one molecules at a time, and then we'll dissociate the molecules into multiple fragments, and we measure with a position and time sensitive detector. Basically, what does it mean? Like when we can retrieve the full 3D momentum information of each fragment later on. And the molecules that we use as an example is on isosazole. It has like 5-member ring with 8 atoms, and then it also have like 2 unique atoms like the oxygen and the nitrogen, so that we can define the coordinate frame later on. Yeah, and the answer is yes. So you can do the same thing with tabletop lasers. Here we detect, so we look at the event where we detect at least like one proton come together with one carbon, one nitrogen, and one oxygen. And then we plot it the same way. We plot the momentum of the oxygen on the x-axis, and then the nitrogen on the top of the xy plane. So you can see on the atom in the molecule. So this is the momentum image of the nitrogen, And then this free distribution corresponding to the free carbons, and also the free distribution here corresponding to the free protons. And then we can replicate this result here using a very simple classical Coulomb explosion simulation. And basically it is showing that like you can look at the molecules of this size, and then the momentum image looks pretty clear and localized, and then you can now so so that you can obtain the similar result compared to X-ray. So but like we don't stop there, we also want to look at the other plane, right? So you can ask what happened in not in the molecular plane, but like the our plane motion. And then what we found out is that like you can take these molecules, rotate 90 degrees, and then look at like the other on the three principal planes, and then you what we found like on those look pretty localized in the molecular plane. If you look at our the plane component, the distribution looks much broader, meaning that the molecules tend to vibrate and exhibit a lot of vibration in our plane. And then when you look at the other projection where the other carbons start to appear here, then you can see that the middle carbon also start in the momentum image. And then you can also see that this carbon somehow tend to vibrate less than the other two carbons. Like it looks more localized. And these 3D momentum information will be more important when you look at non-planar molecules like that. Yeah, so of course we made a 3D momentum, so we just put in a 3D scatter plot. It's just easier to visualize some our plane component and look at non-planar molecules later on. So we are not there yet, but I mean like our ultimate goal is at some point in the near future we want to start with the ring molecules and then decide the molecules into some non-planar configuration and try to make the molecular movie in 3D. Not there yet, but we are pretty close, I could say. Yeah, so the next question is like, how about other molecular structure? So we start with the ring molecules. So we want, we are like, okay, now if we cite this test, like what other structure that it will form after that, right? So, and of course, like one structure, like you can open the ring and form another open chain structure. You can also form some sort of like smaller ring and then with a chain attached to it. So at the first step, we just look at this structure and then we just pick some molecules that have similar structure to those structures, and then try to see whether we can still have the free momentum image of these molecular structure. And the answer is also yes. So you can so what we found like when we look at this structure, we also still also see like very clean momentum image with distribution corresponding to different atoms in a molecule. Carbon we color like purple here. And it's somehow like it's in momentum state again. We don't do the inversion to real state, but somehow it's captured a lot of detail about the molecules, and they also look different. So hopefully we can distinguish them in a time result measurement. Now it's captured a lot of detail about the molecules, and they also look different. So hopefully we can distinguish them in a time result measurement when we induce all sort of different structure. Yeah, and if we want to do pump probe measurement, then we also want to do it in a reasonable amount of time. So I show here basically like how long does it take to apply this momentum pattern, and with the 3 kilowatt laser, it took us like around 1 hour or less to have this pattern. So hopefully like our lab is going to get a new 100 kilohertz laser, so we hope to increase the statistic and review the acquisition time so that we can follow the probe dynamics in as a constant delay. Okay, so of course, like the real question, like, can we really make molecular movie that show the motion of the atom within the molecules? And I will give you two examples. The first example is on, again, on a small molecules, just a diatomic sulfur dioxide. So in this experiment, basically, we start with the neutral sulfur dioxide, and then we use ions to ionize the neutral SO2 into its cationic state, like SO2 plus. And because the equilibrium geometry of the ionic state is different from the neutral, and the bond length is similar, but the angle is different, you will induce the bending motion of the molecule, so it vibrates like that. And after some time, we come up with the second pulse called the pro-pulse, where we promote it into higher charge states, and then it will dissociate into O+, and S+, and then we detect these fragments in our detector and try to retrieve the information about the induced wave package here. Yeah, so and then so this plot here shows you the angle between the two momentum vectors of the two O+, and you can see this nice oscillation. Basically, if you do the FFT, it's corresponding to the frequency of the bending vibration. And then if you measure the kinetic energy of the S+, then you will see it also oscillate at the same frequency, but it oscillates out of phase with this angle here, the angle of the two O+. And this is easy to understand because like when the angle is small, basically the two O+ will push the S+ in like same direction, so you have more kinetic energy. And then when the angle is big, then the Coulomb force between the two O+ sort of like cancel each other out to some extent, so you have less energy, and then you will see our phase oscillation. Then we put all of this information together in the Newton map, and then we get this. So what I show you in purple is the experimental data in momentum space, and in this, so I basically just pick out one vibration cycle and then just keep the movie repeated. But in this, you can see in this particular case, the momentum space image look very localized. It also vibrates, and it's also reflect like very closely give you the image of the molecules that are vibrating, and it's somehow very close to the Born and state model that we have in our head. Yeah, so it looks pretty good. Of course, like we are working on trying to invert this momentum image into the real space, but we are working on that. It's not done yet. So anyway, it gives you a very direct information about how the molecule vibrate at a function of time. And then now you have that information, you can start to correlate what you know here with other observable that you have in the lab. For example, on the right, I show you on the top panel, I show you the yield of the S+ and O2+ channel at a function of delay. Basically, what is saying is like in this channel, somehow the two oxygen come together and stick together and form molecular oxygen or molecular oxygen ion, like O2+. And if you compare it with how the wave vectors oscillate, you can see that in the lower plot, you can see the angle between the two O+ momentum. And you can see whenever the angle gets small, then there's a higher chance that you will form molecular oxygen ion. And it gives you very like intuitive picture about the dynamics that going on. Yes, so in the second example, firstly, we want to look at the green opening reaction induced by the ultraviolet pulse of full run. Yeah, I should use the molecules that I start with at the beginning, but it's not done yet, so I just show these molecules instead. So in this experiment, we use the UV pump at like 198 nanometer, about 100 femtosecond. below 10 to the 12 watt per centimeter square to excite the photon molecules into the second excited state, and then it will go under the non-adiabatic transition that will drawn down and then lead to free opening dynamics. And then again, like at the function of delay, we come up with the second points, like the pro points, 790 nanometer, about 28 femtosecond higher intensity, explore the molecules and look at the Newton plot, the image of the molecules in momentum space. And this is what we have. So you can see as a function of time when we start from the left and to the right, you can see that these atoms corresponding to this carbon start to go toward the center. And of course, like, there's some blurry in the other atom as well. So of course, like in the pump probe measurement, you have contribution from pump and unpump molecules, so the interpretation is a little bit more complicated. But what's basically the basic idea is like what is telling you is that like this one this carbon get very low momentum after something, and the reason it get low momentum is because you found some sort of a linear chain over here, so that carbon stuck in the middle, and the Coulomb force is like far away from these atoms, so it's stuck in the middle, and then the Coulomb force from this carbon and this carbon cancel each other out, and that's why it gets very low momentum. So of course, like momentum space here, inversion to real space would be much better. We are working on that, and then we also do have initial population to sort of like elucidate more of the experimental result here. Yeah. In conclusions, we investigated the scalability of Coulomb explosion imaging to intense tabletop lasers, non-planar molecules, and 3D momentum space, and under these conditions, we obtain comparable clarity compared to recent result from the X-ray free electron laser. And we also saw that it's feasible to follow structural changes by tracking the motion of individual atoms within the molecules. Of course, the inversion from momentum space to real space is non-trivial and needs more attention. Our group and also a few more groups also working on this. But even in momentum space, it gives very pretty nice intuitive image about how the molecule move at the function. And with that, I would like to thank everyone who contributed to the works, and also thank you for your attention.